Hi, Calc BC. Today we're going to be talking about lesson 8.3, Logistic Models with Differential Equations, Part 2. This is the last lesson of new material that we're going to do this whole school year. So that's pretty exciting. We're in College Boards Unit 7. We are still in 7.9, Logistic Models with Differential Equations. And here's the background today. So you can see all of this stuff is essential knowledge. We kind of went over this last time. But in the last lesson, we talked a lot about the derivative as a differential equation for a logistic model, but we didn't actually talk about what is the equation of the model itself. Like what's the initial equation, not the derivative. So today we're going to be talking about that. We're going to talk about how do we find the, like position function, as you will, of the logistic model. And yeah, so let's get over to the notes and check it out. All right, so here's our first question. And only question. We have parts A, B, and C. The rate at which the flu spreads through a community is modeled by the logistic differential equation dp dt equals 0.001 p times 3000 minus p, where t is measured in days. So that type of equation should look familiar, right? That's the differential equation model for logistics. And part A says if p of 0 equals 50, solve for p as a function of t, all work must be shown. So now we're talking about solving for p. So we're looking for not dp dt, but the original p of t function. So the integral of this, in other words. And we have an initial condition. So we're even going to be able to solve for the constant when we get there. So there will eventually, at the end of this part, be a formula that we're going to use so that we don't have to go through all the steps in order to find the original function. But this time, just for this one time, we're going to go through all the steps to show how we get the general solution of a logistic model. So we'll start, though, with this equation. So I'm going to write that out. Okay, and something that's important to note is if we think about dp dt as you may have originally learned it, dy dx, notice the p is in place of the y. So think of these p's as like y's. So it's not like we can just integrate, like typically using our normal integration rules. We're going to have to think of this as a differential equation. It is indeed a differential equation. So what I'm going to do is I'm going to move the p and the 3000 minus p to the left so that it could be paired with the dp. And we're going to move the dt to the right. So we're going to end up with 1 over p times 3000 minus p dp equals 0.001 dt. So I moved the dt to the right side, moved the p and the 3000 minus p to the left side. So now, normally in a differential equation, we would integrate both sides, but this isn't really ready to be integrated yet. It's not going to work out well. And so the first thing I'm going to do might not be intuitive, but I'm telling you it's going to make the rest a lot easier if we multiply both sides of our current equation by 3000. So this numerator is going to change to 3000, and we're going to do 0.001 times 3000. That is the carrying capacity in this question, and it's going to make the next step easier. So I'm going to do 3000 over p times 3000 minus p dp equals 0.001 times 3000 is 3 dt. Okay. So now we're going to try to integrate both sides, but this is going to be more easily integrated if we use partial fraction decomposition first. So let's try that. So we'll have something over p plus something over 3000 minus p. And remember, we can do the cover-up method here. So if p was 0, that would be the convenient p value to plug in. So I can cover up the p, plug in 0 for everything else. We get 3000 over 3000. So the first numerator is 1. And for the second factor, the convenient p value is going to be 3000. So if I cover up this factor, plug in 3000 for p, I'm going to get 3000 over 3000, or 1 once again. That's why we wanted that numerator to be 3,000 so that these partial fractions ended up a lot nicer and didn't have like 1 over 3,000 as a numerator, right? So now we're at a point where we can integrate both sides. So I'm going to initiate the integration. And on the left here, we're going to end up with the natural log of the absolute value of p. And we're going to end up with the natural log of the absolute value of 3,000 minus p. And because the p is negative here, we're going to have to multiply by -1. So this becomes minus. And on the right side, we end up with 3t. And then we got to put our plus c, right? Okay, so the natural log minus another natural log can be combined using division. So we can combine this to the natural log of p over 3,000 minus p. And then it really, for our purposes, is going to be nicer if this fraction is flipped. So think about in a natural log, if we want to flip a fraction, you would have to raise it to the -1 power. And then a -1 power can be brought in front of the natural log. So I'll do this, I'll write out the steps here so that we don't get confused. So first we've got natural log of 3,000 minus p over p to the -1. And then the -1 can come in front to give us negative natural log of 3,000 minus p over p. And then I'm going to want that negative on the other side. So I'm going to multiply everything by -1 now. So we get natural log of 3,000 minus p over p equals -3t minus c. Okay. Then I am going to try to get rid of this natural log. So I'm going to go e to the natural log of 3,000 minus p over p equals e to the -3t minus c. So we end up with 3,000 minus p over p equals e to the -3t minus c. And I don't want this, constant to be locked up here in the exponent. So let's think this through here for a second. If we have two portions of our exponent that are either added or subtracted, we could separate this into e to the -3t times e to the -c. Since c is a constant, e to the -c is, just another version of a constant. So what we're going to do here is remove that -c from the exponent and just plop it in front of the e. So we'll have 3,000 minus p over p equals c e to the -3t. And this is not the same c as up here. So sometimes we would put like a c2 to show that it's like a different constant. I'm not going to continue to write that too, but you just need to know we brought the c down because it was e to the -c is just a constant anyway. So we might as well just call it c. But just know it's a different c than the step before. Okay. And then we can multiply this p to the other side. So we end up with 3,000 minus p equals p times ce to the -3t. And then we can add p to the other side. So that's just 3,000 equals. I'm moving up to the right side here. So we have 3,000 equals p plus p times ce to the -3t. And then we can factor out a p. So we get 3,000 equals p times 1 plus ce to the -3t. And then we can divide by 1 plus ce to the -3t to solve for p. So we get p equals 3,000 over 1 plus ce to the -3t. Okay. So the next step is going to be to solve for this new constant that we have in here. We were given an initial condition, remember, when it said p of 0 equals 50. So we could say that 50 equals 3,000 over 1 plus c e to the -3 times what, 0? Yes. We're plugging in 0 for t. So e to the 0 is just 1, so this becomes 1 plus c So we get 3,000 over 1 plus c equals 50. And so then we end up with what? 3,000 equals 50 times 1 plus c. Divide by 50, and we get 60 equals 1 plus c. So 59 equals c. So our final version of this formula, I'm going to write over here, we get p of t equals 3,000 over 1 plus 59 e to the negative 3t. Okay. So although that was a lot of work, there wasn't really any new concepts, right? We talked about partial fraction decomposition. Everything else was just kind of manipulation using integration and algebra concepts that we've known for a while. It was just a lot. But there's a formula, so we don't have to do all of this work every time. If we graph this, though, we'll end up with, a logistic looking model. And we're going to apply that answer down in parts B and C. But before we get there, I just want to kind of take a pause, take a breather, and say that in general, let's write a rule. We're going to say in general, for the differential equation in form that we know from last lesson, dp dt equals k times p to the L minus p, we could say that the general solution has the form p of t equals L over 1 plus c e to the negative L k t. And that's exactly what we used, or what we ended up with up here, right? L was 3,000, c was some new constant that we had to figure out, and then up here multiplied by t was negative 3, which is negative L times k. Those come straight from the original, so it's 0.001 times 3,000 equals that negative 3 that we ended up with up here, okay? So I'm going to box this because this is something that we should memorize. And I'm going to write a couple extra pieces down here. I'm going to say where k, which is a constant, and L, which is the carrying capacity, can be transferred directly between the two equations. So this k is the same as this k, this L is the same as this L and this L. So that's what we're working with there, okay? So now we have the general solution and the derivative for a logistic model. So let's apply this in part B and part C. So part B, use your solution to part A and your graphing calculator to find the size of the population when t equals 2 days. So we're going back to this example that we have up here. This is the model we're using. And t is number of days, and we're given t equals 2, so we're going to plug in 2. So we got p of 2. And all I'm doing is plugging in 2 for t. So it's going to be 1 plus 59 e to the negative 3 times 2. And all I'm doing is plugging that into my graphing calculator, and I end up with 2,617.238 is the population size. And that's it. Not too bad compared to part A. Part C, use your solution to part A and your graphing calculator to find the number of days that have passed when 2,400 people have contracted the flu. So now we're plugging in 2,400 for P. So we're going to have 2,400 equals that model that we came up with. So 3,000 over 1 plus 59 e to the negative 3t. This time we're solving for t. So I'm going to multiply that denominator to the other side. So we end up with 2400 times 1 plus 59 e to the negative 3t equals 3000. I'm going to divide by 2400, so I get 1 plus 59 e to the negative 3t equals 5/4. I'm going to subtract 1, and I'm just going to continue to solve for t. So I subtract 1, and I get 59 e to the negative 3t equals 1/4. Then I'm going to divide by 59, so I end up with e to the negative 3t equals 1 over 236. Then I'm going to take the natural log of both sides. That's how I get rid of this e right here. So I do the natural log of e to the negative 3t equals the natural log of 1 over 236. Natural log and the e cancel because natural log of e is 1, and this exponent can be brought down in front. So we get negative 3t equals the natural log of 1 over 236. Then I'm going to divide by negative 3, and finally we have the t isolated. So then we have the natural log of 1 over 236 divided by negative 3. And once we do that in our calculator, we're going to end up with 1.821, and t is measured in days. So there we go. We've officially finished. So that's how you do it. Yeah, and now you know everything there is to know about Calc BC. All right, so let me know if you have any questions on the worksheet. Thank you very much for watching. Have a great day.